Hello, and welcome to Space for Sleep. On September 15th, 2017, a radio signal left Saturn and crossed more than 1 billion kilometers of space toward Earth. The signal was weak, deliberate, and already old by the time anyone could receive it. Radio waves need well over an hour to travel from Saturn to our planet, depending on where the two worlds are in their orbits. By the time antennas in Australia heard the final transmission, the spacecraft that sent it no longer existed. Cassini was falling into Saturn. For almost 20 years, the spacecraft had survived launch, interplanetary space, radiation, cold, heat, software problems, mechanical risks, and hundreds of carefully planned encounters. For 13 of those years, it had orbited the ringed planet, using Titan's gravity to reshape its path again and again. It had watched seasons change across Saturn. It had delivered a probe to the surface of Titan. It had flown through water erupting from Enceladus. It had crossed the shadows of the rings and passed between the rings and the atmosphere where no spacecraft had gone before. Now its small attitude control thrusters were firing continuously, trying to keep the high-gain antenna pointed toward Earth as the upper atmosphere grew thicker around it. Cassini was still doing science. Its instruments measured the gas directly ahead. Its radio system transmitted the measurements almost as quickly as they were collected. The spacecraft had no possibility of surviving. The final trajectory had been planned years earlier, and a final distant encounter with Titan had placed Cassini on a path from which there was no return. The end was not an accident. It was the final act of planetary protection. Cassini had discovered that Enceladus contains a salty ocean beneath its ice, an ocean connected to warm rock and supplied with chemical energy. It had shown that Titan contains complex organic chemistry, surface lakes and seas, and a buried water ocean. Those discoveries made both moons scientifically precious. The spacecraft had not been sterilized to the standards required for direct contact with a potentially habitable ocean world and could still have carried hardy terrestrial microorganisms. If it were left in an uncontrolled Saturn orbit after its propellant ran out, it might eventually collide with one of those moons. So the mission that had revealed potentially habitable environments was deliberately destroyed to preserve them. The thrusters reached their limit. Atmospheric force turned the spacecraft away from Earth. The radio carrier disappeared at 4:55 in the morning, Pacific Daylight Time. In mission control at the Jet Propulsion Laboratory in California, a line on a monitor flattened. The team had known exactly when this would happen. The silence still felt sudden. Cassini's last signal ended one mission and preserved the questions that mission had created. To understand why the final moment mattered so deeply, we must return to another period of waiting, 13 years earlier, when the same spacecraft approached Saturn for the first time and no one yet knew whether it would remain there. The date was July 1st, 2004. Cassini had traveled for 6 years and nearly 9 months since leaving Earth. It was moving towards Saturn at tens of thousands of kilometers per hour. To become the first spacecraft to orbit the planet, it had to slow down at exactly the right place, in exactly the right direction, for roughly 96 minutes. A successful engine burn would allow Saturn's gravity to capture it. A burn that ended too early could leave the spacecraft on an orbit too wide or even send it back into interplanetary space. A burn that continued too long could place Cassini too close to the planet. A failure to ignite would turn the entire mission into a single flyby. The spacecraft carried a backup engine, but there would be little time to diagnose a major problem during the encounter. The commands had been prepared in advance. Saturn was too far away for real-time control. A command sent from Earth would take more than an hour to arrive, and the reply would take more than an hour to return. Cassini had to perform the critical sequence by itself. Before the burn, the spacecraft crossed the plane of Saturn's rings through a gap outside the main ring system. Even there, unseen particles could damage instruments or puncture vulnerable equipment. Cassini turned its broad high-gain antenna forward to act as a shield. Then it rotated again, pointing its main engine in the direction of travel. The engine ignited. For the mission team, the most important event was happening beyond immediate observation. Cassini transmitted a simple radio tone rather than a continuous explanation of what its systems were doing. Engineers watched changes in the signal and waited for the spacecraft to emerge from behind Saturn. The planet filled the sky around it. The rings appeared as enormous bright planes extending into darkness. The engine continued burning. Saturn pulled. Cassini slowed. After approximately 96 minutes, the engine stopped. Cassini had entered orbit. The mission team received confirmation after the unavoidable light-time delay. Years of construction, political negotiation, launch preparation, and interplanetary navigation had reached one narrow point, and the spacecraft had passed through it correctly. 13 years at Saturn became possible because one engine fired as planned. The mission had not begun in 1997 when Cassini launched. Its intellectual beginning reached back to the Voyager encounters with Saturn in 1980 and 1981. Voyager 1 and Voyager 2 transformed the ringed planet from a distant telescopic image into a system of worlds. Their cameras revealed braided rings, narrow gaps, small moons, atmospheric bands, and the orange haze of Titan. But a flyby is a brief crossing. A spacecraft arrives, collects data for days, and continues outward. The Voyagers showed enough to make a longer mission necessary. Titan was especially compelling. It was larger than the planet Mercury and wrapped in a dense atmosphere rich in nitrogen and methane. Its surface remained hidden beneath haze. The atmosphere might preserve chemistry related to processes that occurred on the young Earth before life changed our planet. Saturn's rings raised equally deep questions. Were they ancient, formed with the planet, or younger debris from a broken moon? Why did sharp gaps remain open? How did tiny moons shape ring edges? Why did dark radial spokes appear and disappear across the B ring? The other moons appeared unexpectedly diverse. Iapetus had one dark hemisphere and one bright hemisphere. Mimas carried a crater so large that the impact nearly disrupted it. Enceladus looked unusually bright and geologically varied. Tethys, Dione, Rhea, and Hyperion each presented their own puzzles. A single spacecraft could not merely visit Saturn. It would have to live there. In the early 1980s, American and European scientists proposed a joint mission, a Saturn orbiter accompanied by a probe that would enter Titan's atmosphere. The partnership became Cassini-Huygens. NASA's Jet Propulsion Laboratory designed, assembled, and managed the Cassini orbiter. The European Space Agency developed the Huygens probe and the equipment needed to communicate with it. The Italian Space Agency provided Cassini's enormous high-gain antenna and other radio system contributions. Scientists and engineers from many nations built instruments and planned observations. The name joined two histories. Christian Huygens discovered Titan in 1655 and correctly explained that Saturn is surrounded by a thin, flat ring. Giovanni Domenico Cassini discovered Iapetus, Rhea, Tethys, and Dione, and identified the broad division in the rings that now carries his name. Their 17th-century telescopes had turned points of light into a planetary system. The spacecraft would turn that system into landscapes, weather, chemistry, and time. International cooperation made the mission scientifically richer, but it also made development more vulnerable. Budgets changed. Political priorities shifted. The program faced criticism for cost and technical ambition. In the United States, opponents questioned whether one mission should carry several $billion of expense across development, launch, crews, and operations. The spacecraft was large because the task was large. Cassini-Huygens weighed about 5.5 tons at launch, most of it propellant. Its main body stood more than 6 meters high. The high-gain antenna was 4 meters across. A long magnetometer boom extended away from magnetic interference generated by the spacecraft itself. Other booms and instruments gave the vehicle an irregular shape that looked less like a streamlined machine than a traveling laboratory. Cassini carried 12 scientific instruments. They could image in visible and infrared light, analyze ultraviolet radiation, study dust, plasma, magnetic fields, radio waves, gases, and charged particles, probe atmospheres by sending radio signals through them, and map Titan's hidden surface with radar. Huygens carried 6 instrument packages of its own. The probe would have only a few hours to work. Cassini would work for years. Power presented a fundamental problem. At Saturn, sunlight is roughly 1% as intense as it is near Earth. Solar arrays capable of operating the entire spacecraft would have been extremely large and heavy by the technology of the time. Cassini used 3 radioisotope thermoelectric generators. Heat from the natural decay of plutonium dioxide was converted into electricity. At launch, the generators supplied hundreds of watts, slowly declining over the mission as the fuel decayed and the thermoelectric materials aged. The plutonium made the mission possible and controversial. Cassini's trajectory required an Earth gravity assist in 1999. The spacecraft would return close to the planet, carrying its radioisotope generators. Some members of the public feared an accident and protested the flyby. NASA analyzed launch failures, atmospheric re-entry scenarios, and containment. The radioisotope fuel was not a bomb and could not produce a nuclear explosion, but the possibility of radioactive release demanded serious engineering and public explanation. The flyby proceeded safely. The concern revealed something important about outer planet exploration. A mission to Saturn is not isolated from Earth. Its design choices, risks, and costs belong to the society that launches it. Cassini left Cape Canaveral on October 15, 1997, aboard a Titan 4B rocket with a Centaur upper stage. The launch was only the first acceleration. No available rocket could send a spacecraft this massive directly to Saturn on a practical trajectory. Cassini needed the planets. It flew past Venus in April 1998. It returned for a second Venus encounter in June 1999. 2 months later, it passed Earth at an altitude of roughly 1,200 kilometers. Then it continued toward Jupiter, arriving at the giant planet in December 2000. Each encounter was a gravity assist. The phrase can sound as if a planet pulls a spacecraft forward for free. The deeper description involves exchanging orbital energy and momentum. A spacecraft approaches a moving planet, curves through the planet's gravitational field, and departs with its velocity changed in the sun-centered frame. The planet changes too, but by an amount too small to notice because its mass is immense. The sequence of Venus, Earth, and Jupiter gave Cassini the energy needed to reach Saturn with the propellant it carried. The trajectory took longer than a direct flight, but it turned planetary motion into part of the launch system. During the cruise, teams tested instruments, updated software, corrected the path, and periodically woke Huygens to verify that it remained healthy. The spacecraft crossed the asteroid belt without drama and used the Jupiter encounter as an early scientific campaign. Cassini and Galileo, which was already orbiting Jupiter, observed the Jovian system at the same time. 2 spacecraft viewed the giant planet from different positions, creating a coordinated study of the magnetosphere, atmosphere, rings, and moons. Jupiter was rehearsal and discovery. Then Saturn grew larger. In June 2004, before orbit insertion, Cassini passed Phoebe, a dark, irregular moon traveling in a distant retrograde orbit. Images revealed a battered body rich in ice beneath its dark surface, probably captured from the outer solar system. Phoebe was the first close Saturnian encounter, and a reminder that the mission would not follow a simple list. Each object would change the meaning of the next. The spacecraft approached the rings. The main engine fired. Saturn captured Cassini. And almost immediately, the system began to overturn expectations. The first major target was Titan. Titan had shaped the entire mission architecture. Its dense atmosphere made direct descent possible. Its gravity also made Cassini's long tour possible. The moon was both a world to explore and the mission's steering wheel. Cassini did not carry enough propellant to reshape its orbit hundreds of times by engine burns alone. Instead, navigators used targeted Titan flybys. Each close pass bent the spacecraft's path, changing orbital inclination, period, and direction around Saturn. A moon became a propulsion system. Over the mission, Cassini completed 127 targeted Titan flybys. The encounters moved the spacecraft toward other moons, high above the ring plane, close to Saturn, and eventually toward its final plunge. This dependency made Titan more than one destination among many. The mission returned again and again, building a record impossible for a single flyby. Before Cassini, Titan's surface was almost completely hidden. Visible light could not penetrate the thick orange haze. The atmosphere is denser at the surface than Earth's and composed mostly of nitrogen, with methane playing an important chemical and climatic role. Sunlight breaks methane apart high in the atmosphere. Reactions build larger hydrocarbons and nitrogen-bearing organics, creating haze particles that settle downward. Cassini carried radar because radar waves could pass through the haze. During the first close flyby in October 2004, the radar instrument began revealing terrain. Bright and dark regions formed patterns unlike any familiar planetary map. Later swaths showed dunes, channels, mountains, plains, craters, and shorelines. The coverage accumulated slowly because each radar pass mapped only a strip of the enormous moon. Titan became a world assembled piece by piece. Near the equator, radar revealed immense fields of long, parallel dunes. They stretch across thousands of kilometers and are made not of quartz sand, but probably organic particles produced in the atmosphere, processed on the surface, and moved by winds. Near the poles, the landscape changed. Dark, smooth regions filled depressions. Shorelines curved around bays and islands. Radar reflections showed liquid surfaces. Titan possesses lakes and seas of methane and ethane. Kraken Mare is larger than the Caspian Sea by area. Ligeia Mare is deep enough in places to contain an enormous volume of liquid hydrocarbons. Smaller lakes cluster around the North Polar region, some with steep-sided boundaries that may record dissolution or collapse in icy bedrock. Titan became the only world beyond Earth known to have stable, open liquid on its surface. The chemistry is alien, but the processes are recognizable. Methane evaporates. Clouds form. Rain falls. Rivers flow. Lakes rise and fall. Waves may move across seas, though Cassini found surprisingly smooth surfaces during many observations. On Earth, water cycles among ocean, atmosphere, land, and ice. On Titan, methane performs a similar climatic role at a temperature near -180 degrees Celsius. Water on Titan behaves more like rock. Water ice forms the crust. Methane and ethane act as liquids. Organic particles act as sediment. The analogy to Earth is powerful precisely because the materials are so different. Cassini observed clouds moving through Titan's atmosphere and changes consistent with rainfall wetting the surface. It watched seasonal patterns shift as Saturn and its moons traveled from southern summer toward northern summer. A year at Saturn lasts about 29.5 Earth years. Cassini remained long enough to witness nearly half of that seasonal cycle. The North Polar region was dark during the spacecraft's arrival. Over the years, sunlight returned and the northern seas emerged into view. Clouds changed latitude. Atmospheric circulation reorganized. Surface brightness shifted after storms. A flyby would have found one season. An orbiter watched a climate. But Cassini alone could not provide the view from beneath the haze. That task belonged to Huygens. On December 25, 2004, Cassini released the probe. Springs pushed Huygens away, beginning a 22-day coast toward Titan. The probe had no engine to correct a major mistake. Its entry angle depended on Cassini's release and navigation. Cassini then changed course so it would pass Titan at the right position to receive the probe's radio transmissions. Huygens slept during the coast. On January 14, 2005, a timer woke it before atmospheric entry. The probe struck Titan's upper atmosphere at several kilometers per second. A heat shield absorbed the violence. Atmospheric drag slowed the capsule. Parachutes deployed in sequence. The protective front shield fell away. Instruments opened to an orange world. Huygens began descending through layers no machine had sampled before. The descent lasted about 2 hours and 27 minutes. Wind pushed the probe sideways. Its spin changed unexpectedly and even reversed direction during part of the fall, a behavior explained only years later through tests of airflow around the parachute system. Cameras looked downward and outward. At first, the haze revealed little. Then the surface emerged. Branching channels ran from brighter highlands into darker lowlands. Rounded forms resembled drainage networks. The terrain looked carved by flowing liquid. The images were not proof of rain falling at that moment, but they showed a world shaped by methane rivers. Cassini, flying overhead, listened for Huygens. The communication system carried an uncomfortable history. Years before arrival, tests had revealed that Doppler shifts between the probe and orbiter could have distorted data because of a design oversight in the receiver. Engineers changed the Cassini trajectory to reduce the relative motion and protect the link. One operational mistake remained on landing day. One of Cassini's 2 Huygens receiver channels was not activated. Data intended for that channel was lost from the orbiter link, including part of the Doppler wind experiment. But the mission was not silent. The other channel worked. Radio telescopes on Earth detected Huygens directly and helped recover wind information from the faint signal. The incident became a lesson in fragility and redundancy. A mission can succeed while carrying scars from what almost failed. Huygens descended below the haze. The ground expanded beneath it. The probe struck the surface, made a shallow depression, bounced, slid, and wobbled before coming to rest. It had landed on Titan. No spacecraft had ever touched a world in the outer solar system. The surface was neither a methane ocean nor solid metal hard ice. It behaved more like damp sand or compacted snow with a firmer layer beneath. Rounded water ice cobbles lay nearby, shaped as if they had been transported by flowing liquid. Huygens continued transmitting from the surface for more than an hour while Cassini remained above the horizon. Its lamp illuminated the ground. Instruments measured temperature, pressure, and composition. Methane appeared to increase near the surface, consistent with moisture or methane-rich material disturbed by the warm probe. Then Cassini moved beyond the probe's transmitting beam and soon below Titan's horizon, ending the relay of full scientific data. Huygens continued transmitting from the surface, and radio telescopes on Earth detected its carrier for more than 3 hours after landing, although they could not decode the complete instrument stream. The probe's scientific life had lasted only hours. Its images became a key for interpreting years of Cassini radar and infrared observations. Channels seen from orbit could now be understood as drainage systems. Dark plains could be compared with the landing site. Atmospheric models gained direct temperature and wind measurements. The descent turned Titan from a hazy moon into a place where a machine had fallen through weather and rested among rounded stones. Titan alone could have justified the mission. Cassini did not stop there. The spacecraft's early tour included Enceladus, a moon only about 500 kilometers across. Voyager images had shown a bright surface with regions of different ages, suggesting past resurfacing. Yet the moon was small enough that it should have lost internal heat long ago. No mission plan expected Enceladus to become the most urgent astrobiological discovery at Saturn. In February 2005, Cassini's magnetometer detected a disturbance near the moon. Saturn's magnetic environment appeared to be interacting with gas or charged particles released from Enceladus. A body with such weak gravity cannot hold a substantial atmosphere for long. If gas was present, something had to replenish it. Later flybys moved closer. Images of the south polar region revealed long, nearly parallel fractures crossing terrain with few impact craters. The fractures were warmer than the surrounding surface. Then Cassini looked back toward the moon with the sun behind it. Tiny particles scattered light forward. A plume appeared above the South Pole. Enceladus was erupting into space. The discovery immediately changed mission priorities. Flybys were redesigned. Some passed directly through the plume. Cassini lowered its altitude to tens of kilometers above the surface and turned instruments toward the oncoming gas and ice. The spacecraft had not been sterilized or designed as a life detection laboratory. Its instruments were built to characterize particles, fields, and chemistry across the Saturn system. Yet the moon was delivering samples from its interior without requiring a lander or drill. Cassini detected water vapor, ice grains, salts, organic compounds, carbon dioxide, methane, ammonia, and molecular hydrogen. Silica nanoparticles implied that water had interacted with rock at elevated temperatures. Gravity measurements and the moon's rotational wobble supported a global subsurface ocean rather than one small regional reservoir. The ocean was salty. The rocky interior appeared porous. Water could circulate through the core, react with minerals, and return carrying chemical energy. Molecular hydrogen strengthened the case for active water-rock reactions resembling serpentinization. On Earth, microorganisms can use hydrogen and carbon dioxide to produce methane and obtain energy in darkness. Cassini had not found life. It had found a known ocean, available chemical ingredients, and a plausible energy source. That distinction mattered. Before the mission, Enceladus was one icy moon among many. After Cassini, it became one of the most accessible places in the solar system to search for present-day life. The transformation happened step by step. A magnetic anomaly suggested gas. Images revealed fractures. Infrared measurements found heat. Backlighting revealed plumes. Dust analysis found salts. Radio science and libration indicated an ocean. Silica and hydrogen pointed toward hydrothermal chemistry. No single observation created the conclusion. Independent measurements converged. This is how a long orbital mission changes science. It does not merely take a better picture. It returns to the same object with new questions created by the previous encounter. Cassini ultimately completed 23 targeted Enceladus flybys. Not every pass crossed the plume. Some mapped surface geology, measured gravity, watched thermal changes, or sampled the surrounding environment. Each encounter required a different spacecraft orientation. A camera wants one direction. A mass spectrometer wants to face the incoming gas. A radio science experiment may need the antenna pointed precisely toward Earth. The spacecraft could not satisfy every instrument at once. Teams negotiated priorities and designed sequences months in advance. At Saturn, discovery was partly the art of choosing what Cassini would look at and what it would temporarily turn away from. Enceladus also explained part of Saturn's ring system. The broad, diffuse E-ring surrounds the orbits of several moons. Cassini showed that the plume continuously supplies it with ice grains. A small moon feeds a planetary ring. Some particles escape Enceladus and spread around Saturn. Others fall back, coating the surface with fresh ice and helping make the moon one of the brightest objects in the solar system. The plume connects ocean, surface, ring, magnetosphere, and planet. A discovery that began at one moon became a system-wide process. This was the pattern of Cassini's 13 years. Nothing existed alone. Titan's atmosphere exchanged material with space. Enceladus supplied the E-ring. Ring particles interacted with tiny moons. Saturn's magnetic field trapped charged particles that altered icy surfaces. Moons raised waves in the rings, and the rings recorded vibrations from deep inside Saturn. Its deepest lesson was that Saturn had to be understood through relationships rather than isolated bodies. Navigation made those relationships visible. Cassini completed 294 orbits around Saturn. Those orbits did not repeat like a satellite circling Earth at one fixed altitude. Some lasted days, others lasted months. Some remained near the ring plane, others rose far above it. Titan flybys changed the geometry repeatedly. A close approach could tilt the orbit, lower the next periapsis, or aim Cassini toward Enceladus, Iapetus, Rhea, Dione, or a ring observation. The mission used less propellant than such variety seems to require because Titan supplied gravitational turns. This made every Titan encounter part science and part navigation. If the flyby altitude or timing were wrong, later observations would shift. One encounter could determine months of future geometry. The navigation team used optical images of moons and stars, radio tracking from the Deep Space Network, and models of Saturn's gravity to place Cassini where it needed to be. Commands were uploaded well in advance. The spacecraft executed them without a live pilot. A camera exposure lasting seconds might depend on years of trajectory design. Cassini's archive contains hundreds of thousands of images, but behind every image lies a physical appointment between spacecraft, target, sunlight, and Earth. The rings provided the most visually familiar target and one of the hardest scientific problems. From Earth, Saturn's main rings appear smooth. Voyager had already revealed divisions, ringlets, waves, and spokes. Cassini transformed the rings into a dynamic disk. They are made mostly of water ice, with particles ranging from dust to boulders and perhaps larger embedded masses. The main rings extend across hundreds of thousands of kilometers while remaining astonishingly thin compared with their width. In many regions, the vertical thickness is measured in meters or tens of meters. A sheet vast enough to surround a planet can be thinner in proportion than paper. Particles orbit Saturn at different speeds. Those closer to the planet move faster than those farther away. Collisions continually exchange energy and flatten the system toward a common plane. Moons sculpt the edges. Resonances launch waves. Embedded bodies open gaps. Cassini watched this machinery over time. Prometheus repeatedly disturbed the narrow F ring, pulling out streamers and channels. The ring changed from orbit to orbit, never returning to one permanent form. Daphnis traveled inside the Keeler gap and raised vertical waves along the gap's edges. Near equinox, when sunlight struck the rings almost edge-on, those waves cast long shadows. The shadows revealed structures extending kilometers above a ring plane otherwise only meters thick. Tiny Pan occupied the Anki Gap. Closed images showed an equatorial ridge built from material accreted around the moon, giving it a shape compared with a flying saucer or ravioli. Atlas carried a similar ridge. These moons were not simply rocks placed inside gaps. They exchanged material and momentum with the rings around them. Cassini watched propeller-shaped disturbances created by unseen moonlets too small to clear complete gaps. By tracking some propellers for years, scientists studied the orbits and interactions of bodies embedded within the disk. The rings became a laboratory for processes that also occur in disks around young stars. Planet-forming disks are enormously larger and made of gas and dust, but many dynamical principles are related. Gravity produces waves. Small embedded masses carve gaps. Collisions and resonances redistribute material. Saturn offers a nearby disk where those patterns can be resolved in detail. The ring spokes added another kind of motion. Dark or bright radial marks appeared across the B ring, sometimes extending thousands of kilometers. They formed and faded over hours. The leading interpretation involves tiny charged dust grains lifted above the main ring plane by electromagnetic forces. Spokes varied with Saturn's seasons and magnetic environment. Cassini watched them disappear near some periods and return during others. A feature first seen by Voyager became a long-term atmospheric and electromagnetic clock. The origin and age of the main rings remained more difficult. Cassini measured their mass during the grand finale through subtle gravitational effects on the spacecraft. The results showed that the rings are less massive than some earlier estimates, comparable in mass to a fraction of the moon Mimas. Their extraordinary brightness and low abundance of dark contamination led many researchers to infer a relatively young age, perhaps a few 100 million years. A young ring interpretation creates a dramatic history. A large icy moon may have been disrupted by a collision or torn apart after moving too close to Saturn. The debris spread into rings, and subsequent evolution produced the structure we see now. But Cassini did not close the debate permanently. Age estimates depend on how quickly micrometeoroid material enters the rings, how dark contaminants mix with ice, how particles are lost, and whether impacts remove some pollution rather than retaining it. Later models suggested that the rings might resist darkening more effectively than assumed, allowing an older age. Other dynamical arguments still support relative youth. The honest conclusion is not that Cassini proved one birthday. It measured the ring mass, composition, pollution, and evolution well enough to turn age into a sharper and more testable argument. This is often what a great mission does. It replaces one vague mystery with several precise ones. The rings are also not permanent. Material moves inward towards Saturn through several processes. Charged grains follow magnetic fields. Neutral particles fall from the ring region. Cassini sampled an unexpected flow of water, organics, and other material during its final close passes. The rate measured during those encounters was substantial, but extrapolating it across geological time is uncertain. Ring inflow may vary. It is safer to say that the rings are evolving and losing material than to assign one exact disappearance date. They are not a fixed ornament. They are an active structure with sources, sinks, collisions, and memory. Some ring waves carry memory of the moons that create them. Others carry memory of Saturn itself. The planet can oscillate internally, and changes in its gravitational field generate subtle spiral patterns in the C ring. By reading those waves, scientists perform ring seismology. The rings behave like an enormous detector laid around Saturn. They can record frequencies that reveal how the planet's interior moves. This unexpected use of the rings helped support a picture of Saturn's deep interior that is not divided cleanly into a small solid core and a separate hydrogen envelope. Instead, heavy elements may be spread through an extended, diffuse central region. The phrase fuzzy core describes a gradual transition rather than a sharp boundary. Cassini's gravity measurements during the grand finale and later analyses of ring waves both contributed to this developing picture. Saturn's center may contain rock and ice mixed with metallic hydrogen across a large fraction of the planet's radius. The mission entered orbit to study a planet surrounded by rings. It discovered that the rings could also study the planet. Saturn itself changed beneath Cassini's attention. At first glance, the planet appears calmer than Jupiter. Its clouds are softer in visible light, muted by haze above the deeper atmosphere. The belts and zones seem less sharply contrasted. Yet beneath that pale exterior, winds move at hundreds of meters per second, storms rise from great depths, lightning flashes through clouds, and enormous structures persist around the poles. Cassini remained long enough to observe weather as history rather than as a snapshot. When the spacecraft arrived, Saturn's northern hemisphere was emerging from winter while the southern hemisphere remained in summer. The rings cast wide shadows across the northern atmosphere. Year by year, the sun moved northward. The ring's shadows narrowed, crossed the equator at the 2009 equinox, and then spread across the south. Cloud colors changed. Temperatures shifted. Storm tracks migrated. The planet's atmosphere responded slowly because Saturn receives little sunlight and stores heat in deep layers. Seasonal effects unfolded across years. Cassini watched almost half a Saturnian year, from northern winter toward northern summer. No earlier spacecraft had remained at a giant planet long enough to do that. At the North Pole, Cassini revealed the hexagon in unprecedented detail. Voyager had first seen this six-sided pattern, but Cassini observed it across wavelengths and seasons. The hexagon is a jet stream surrounding the pole, with a persistent wave pattern that creates six relatively straight sides. It is not a solid object. Clouds move within and around it. The entire structure rotates around the pole, enclosing a powerful polar vortex. Laboratory experiments and atmospheric models can create polygonal patterns in rotating fluids under certain conditions, but Saturn's exact hexagon remains a remarkable natural result of fluid dynamics. As northern spring advanced, the region changed color from bluish tones toward a more golden appearance, probably as increasing sunlight produced photochemical haze. Inside the hexagon, a cyclone turned around the pole. At the South Pole, another vortex displayed an eye-like center surrounded by high clouds. Cassini looked downward into these structures from orbital angles impossible from Earth. The poles became places rather than blurred endpoints on a planet. Then, in December 2010, Saturn produced a storm vast enough to wrap around the world. The Great White Spot began as a bright disturbance in the northern hemisphere. It expanded rapidly, generating a turbulent head and a long tail that eventually encircled the planet. Lightning produced intense radio emissions. Clouds carried material upward from deep atmospheric levels. The storm altered temperatures high above the visible clouds and created chemical changes that persisted after the main visible disturbance faded. Cassini observed the event from beginning through decline. A giant Saturn storm of this class appears roughly once per Saturn year, though timing varies. Earlier examples had been observed from Earth, but never with an orbiter measuring multiple layers and wavelengths. The mission watched a planetary atmosphere reorganize itself. The storm also demonstrated why duration matters. Had Cassini ended after its original 4-year mission in 2008, it would have missed the 2009 equinox, the enormous 2010 storm, the North Polar changes, and many later discoveries at Enceladus and Titan. The prime mission was extended first through the equinox and then through the solstice. Each extension carried engineering risk. Instruments aged. Reaction wheels, thrusters, heaters, electronics, and propellant had finite lives. Radioisotope power declined slowly. Teams had to decide how to spend remaining capability. The spacecraft repeatedly outlived the assumptions of its original schedule. Its continued survival turned time into an instrument. Saturn's magnetosphere provided another enormous system to measure. The planet's magnetic field creates a cavity in the solar wind that extends far beyond the rings and moons. Charged particles move along field lines, interact with atmospheres and icy surfaces, and generate radio emissions. Cassini crossed boundaries where the solar wind meets Saturn's magnetic influence. It measured plasma populations, energetic particles, and changing conditions as solar activity and Saturn's seasons varied. Titan often orbited within the magnetosphere, where Saturn's plasma interacted with its upper atmosphere. At other times, changing solar wind pressure altered the environment. Enceladus supplied neutral water molecules and charged particles, profoundly affecting plasma around the planet. The magnetosphere was not an empty bubble. It was filled and modified by the moons. Cassini also observed auroras around Saturn's poles. Charged particles traveling along magnetic field lines entered the upper atmosphere and produced ultraviolet and infrared emissions. The auroras responded to both the solar wind and internal magnetospheric processes. They could brighten, shift, and form arcs around the planet. One of the mission's strangest magnetic findings concerned Saturn's rotation. On a rocky planet, one can track surface features to measure the length of a day. Saturn has no solid visible surface. Atmospheric clouds move at different speeds. Scientists had used periodic radio emissions associated with the magnetic field as a clock, expecting the field to rotate with the deep interior. But Cassini found that the radio period changed over time and differed between hemispheres. The signal was influenced by the magnetosphere and seasons, not a perfect measure of the deep rotation. The magnetic field itself was astonishingly aligned with Saturn's rotation axis. Planetary dynamo theories generally expect at least a small tilt to sustain a measurable rotating magnetic signature. Cassini's grand finale measurements placed the alignment within a tiny fraction of a degree. This made the length of Saturn's day harder, not easier, to determine from magnetism. Scientists turned to ring seismology, gravity, atmospheric waves, and other methods. The mission solved many mysteries and exposed the limits of familiar techniques. The moons continued to provide their own surprises. Mimas looked like the least likely ocean world. Its heavily cratered surface appeared ancient and inactive. Herschel crater, about 130 kilometers wide, dominates one hemisphere. The impact that created it nearly shattered the moon. Cassini measured a rotational wobble larger than expected for a simple uniform body. At first, interpretations included an elongated rocky core or a hidden ocean. Years after the mission, more detailed modeling of Cassini data and orbital evolution strengthened the case for a relatively young subsurface ocean beneath Mimas. The conclusion remains surprising because the surface shows almost none of the obvious fractures, plumes, or resurfacing associated with Enceladus. A moon can hide an ocean without advertising it. Cassini's archive changed Mimas after Cassini was gone. This illustrates the difference between data collection and discovery. A spacecraft records measurements under one set of questions. Later scientists ask new questions, improve models, and find meanings the original team could not establish. Tethys showed an enormous impact basin called Odysseus and a canyon system, Ithaca Chasma, stretching across much of the moon. The relationship between the crater and canyon remains debated. One idea suggests that the impact sent stress through the body. Another proposes that the canyon formed as an internal ocean froze and the moon expanded. Dion displayed bright wispy terrain that Voyager had not resolved. Cassini showed that the wisps are networks of tectonic cliffs and fractures, bright because steep ice faces catch sunlight. The moon may have experienced internal activity in the past, and evidence suggests it too may contain a deep ocean. Rhea, the second largest moon of Saturn, carried a heavily cratered surface and a tenuous exosphere containing oxygen and carbon dioxide. Charged particles striking water ice can break molecules apart and release products into space. The atmosphere is far too thin to resemble air on Earth. It is better described as a sparse cloud of molecules. The detection showed that radiation continually processes icy surfaces. Hyperion looked unlike almost any other moon. Its irregular body is deeply cratered, and the interiors of craters appear dark against brighter walls. Its density is low, indicating high porosity. The surface resembles a sponge, partly because weak gravity and impact processes preserve sharp, deep depressions. Hyperion tumbles chaotically. Its rotation cannot be predicted far into the future in the simple way one predicts a regular moon's orientation. Gravitational interactions with Titan contribute to the chaotic state. A spacecraft flyby required careful timing because the moon did not present one stable face. Iapetus carried a mystery more than 3 centuries old. Giovanni Cassini had noticed that the moon was visible on one side of Saturn's orbit, but difficult or impossible to see on the other. He correctly inferred that one hemisphere is much darker and that Iapetus keeps the same face toward Saturn. The spacecraft bearing his name revealed the mechanism in detail. Iapetus' leading hemisphere gathers dark material associated largely with dust from Phoebe and other outer moons. The dark coating absorbs more sunlight, making those regions warmer. Water ice sublimates from the warmer surface and migrates toward colder, brighter areas, where it freezes again. This thermal feedback sharpens the contrast. Dark regions become darker and warmer. Bright regions retain and collect ice. The initial dust coating and later ice migration work together. Cassini also imaged an extraordinary equatorial ridge extending across much of Iapetus, rising in places to heights comparable with major terrestrial mountains. The origin remains uncertain. The ridge may have formed from debris falling from an ancient ring, from internal tectonics, or through another process. Even after a close flyby, Iapetus kept one of its deepest secrets. The tiny ring moons offered a different scale of surprise. Pan and Atlas looked almost artificial because ring material had accumulated around their equators. Daphnis raised waves in the Keeler Gap. Prometheus repeatedly pulled streamers from the F-ring. Methone and Polyne appeared unusually smooth, their weak gravity and fine regolith softening visible features. Cassini discovered and helped name several small moons. Some were found because their gravity created patterns before cameras saw the bodies themselves. The rings could reveal an unseen moon through disturbance. A moon could reveal the ring's density through waves. The system behaved like one coupled machine. The mission also observed temporary features that challenged the boundary between moon and ring material. Small clumps formed and dispersed in the F-ring. Objects collided gently, merged, broke apart, and left trails. Some features survived long enough to receive informal names and then vanished. Saturn's ring system contains creation and destruction on human timescales. A moon need not be billions of years old to be dynamically meaningful. The moons also carried clues about Saturn's past migration. Orbital resonances link their periods. Tidal interactions transfer energy and angular momentum, generally moving moons outward over time while slowing Saturn's rotation by an imperceptible amount. Cassini's precise tracking improved estimates of these migration rates. Some results suggested stronger tidal dissipation inside Saturn than older models assumed. If moons move outward more rapidly, their past resonances and formation histories change. The present architecture may be younger or more rearranged than a static diagram implies. This matters for Enceladus because its resonance with Dione helps maintain orbital eccentricity and tidal heating. It matters for ring origin because a disrupted moon depends on past orbits. It matters for Titan because its migration influences system evolution. Cassini did not merely catalog where moons are. It helped reconstruct how they arrived there. Titan remained central through all of this. Its gravity controlled Cassini's tour, and its science continued changing with each pass. Radar mapped only part of the surface at high resolution, but enough coverage revealed global patterns. Dunes dominate low latitudes. Lakes and seas cluster near the poles. Mountains and bright terrains break the plains. Impact craters are relatively scarce, indicating geological resurfacing. Some broad regions may be built from sediments deposited after ancient basins filled or dried. River channels show branching networks and evidence of erosion. Coastlines reveal past liquid levels. Titan's atmosphere continuously manufactures organic material, but the path from haze to dunes, plains, lakes, and subsurface reservoirs remains complex. Methane itself creates a long-term puzzle. Sunlight destroys atmospheric methane over tens of millions of years, a short interval compared with the age of the solar system. Something must replenish it, or Titan must be observed during a temporary methane-rich era. Possible sources include subsurface reservoirs, methane trapped in ice structures, cryovolcanic release, or long climate cycles. Cassini found suggestive features, but no simple global picture of active cryovolcanoes. The atmosphere may alternate between wetter and drier epochs as orbital conditions and reservoirs change. Titan's present seas could be one phase in a much longer history. Cassini also found evidence for an internal water ocean through gravity, shape, and rotational measurements. The surface hydrocarbon cycle lies above a much deeper layer of liquid water mixed with salts or ammonia. Titan therefore contains two kinds of ocean. At the surface, methane and ethane collect under a nitrogen sky. Far below, water remains liquid beneath an icy shell. The two environments may interact only slowly, if at all. This layering makes Titan one of the most chemically complex worlds known. It is both Earth-like and profoundly un-Earth-like. Huygens showed rounded stones and drainage channels. Cassini showed seas under haze. Neither found life. Together, they showed a world where organic chemistry, weather, geology, and time operate on a planetary scale. Future exploration would no longer ask whether Titan has landscapes. It would ask where to land among them. The future landing site chosen for another mission would not be a methane sea or an icy mountain. It would be a field of organic dunes. Cassini's maps and Huygens' measurements eventually made the Dragonfly rotorcraft concept possible, a machine designed to fly through Titan's dense atmosphere and visit multiple locations. That later mission belongs to another era, but its route begins in the radar swaths and descent images collected by Cassini-Huygens. This is one measure of scientific legacy. A mission changes everything when later missions become imaginable only because its discoveries exist. Cassini's 13 years were not one continuous stream of dramatic revelations. Much of the work was quieter. The spacecraft pointed an instrument. It stored data. It turned toward Earth. The Deep Space Network received a faint signal. Engineers checked spacecraft health. Scientists calibrated measurements. Teams waited for the next orbit. A single observation might take years to interpret. The public often encountered Cassini through finished images, but the mission lived through schedules, files, antenna time, navigation updates, and compromises. Communication capacity was limited. Saturn's distance made the signal faint. Cassini's high-gain antenna transmitted toward giant receivers on Earth, but data rates were tiny compared with ordinary terrestrial networks. Images and spectra accumulated faster during encounters than they could always be sent. The spacecraft carried solid-state recorders and transmitted later. Every bit had a cost in power, storage, and time. Instrument teams proposed observations competing for the same moments. One might want to image Titan's clouds. Another wanted radar mapping. A third wanted to measure plasma. The spacecraft could not point every instrument independently. Planning meetings turned scientific ambition into executable sequences. The long mission created opportunities to revisit mistakes. An image could be taken again under better lighting. A radar swath could overlap an older one. A plume crossing could occur at a different altitude. A moon could be viewed before and after equinox. some opportunities never returned. A particular alignment of moons, rings, sun, and spacecraft might occur once. Cassini's operations combined repetition with irreversibility. The team learned the spacecraft's personality. They knew how long it took to turn, how much heat and orientation created, how star trackers behaved near bright bodies, and how instruments responded after years in radiation and cold. Procedures improved. Unexpected signals became easier to diagnose. The machine and the people aged together. Over its lifetime, Cassini executed millions of commands and hundreds of engine and thruster maneuvers. It collected hundreds of gigabytes of science data and more than 450,000 images. Those numbers are impressive, but they hide the selectivity. Cassini did not photograph every moment. It did not map every square kilometer at the same resolution. The archive is vast and incomplete. Every mission is a set of choices made within limits. This incompleteness keeps Saturn open. There are regions of Titan seen only coarsely. There are Enceladus plume molecules Cassini could not resolve. There are ring structures observed under only a few lighting conditions. There are magnetic variations whose origins remain uncertain. The mission transformed our picture without explaining everything. Its images changed public experience as strongly as some measurements changed science. Saturn had been iconic before Cassini. Through a small telescope, the rings can produce an almost physical shock. The planet looks too perfect to be real. Cassini replaced the static icon with a changing world. Ring shadows moved across cloud tops. Moons passed in front of the planet. Storms appeared and dissolved. The rings became dark silhouettes from the unlit side and brilliant bands from the sunlit side. Images taken near equinox showed the ring plane becoming a narrow line, while vertical structures cast shadows across it. The spacecraft could look back after passing Saturn and see the planet eclipse the sun. In that geometry, faint rings became visible through forward scattered light. The E-rings stretched outward. Tiny particles glowed. Earth appeared as a point beyond the rings. One of the best-known views was assembled from images taken in July 2013 during an event called The Day the Earth Smiled. Cassini photographed Saturn and its ring system while the planet blocked direct sunlight. Earth was visible in the distance as a pale point. People on Earth were invited to look towards Saturn and imagine the spacecraft looking back. No camera could resolve individual faces. The gesture was symbolic, yet it connected two positions in the solar system with unusual clarity. A machine at Saturn photographed the world that built it. The image also revealed the difference between exploration and ownership. Cassini carried human intention, but Saturn did not become ours. The planet remained enormous, cold, and mostly inaccessible. Earth remained a dot. Knowledge increased without reducing scale. The mission repeatedly used eclipses and occultations for science. When a star passed behind Saturn's rings, instruments measured how its light dimmed and changed, revealing particle distributions and ring structure. When Cassini's radio signal passed through Titan's atmosphere before reaching Earth, changes in the signal revealed temperature and density profiles. When the sun or a star disappeared behind an atmosphere, the atmosphere became a filter. Cassini turned obstruction into measurement. Even gravity could be studied through radio. As the spacecraft moved through Saturn's field, its velocity changed. The Doppler shift of the radio signal allowed scientists to detect motions far smaller than ordinary navigation would notice. During close flybys, similar tracking measured moon masses and interior clues. A spacecraft did not need to touch an ocean to infer it. A slight wobble, a gravitational anomaly, or a delayed response to tides could reveal liquid beneath ice. This method made ocean worlds visible through motion. The idea of a Saturn system evolved across the mission because the instruments spoke different languages. Cameras saw form. Radar saw through haze. Spectrometers saw composition. Magnetometers saw fields. Dust detectors felt particles strike. Radio science saw gravity and atmosphere. A conclusion became strong when those languages agreed. Enceladus is the clearest example, but the same method worked everywhere. Titan's seas were dark in radar, shaped like basins, connected to channels, and consistent with atmospheric methane chemistry. Iapetus color pattern matched thermal models and dust sources. Ring waves matched moon resonances. Saturn's interior affected gravity and ring seismology. Cassini was not one observer. It was a coordinated argument traveling through space. The mission's international structure reflected that scientific diversity. Hundreds of scientists participated over time. Instrument teams included researchers across the United States and Europe. The Huygens probe carried experiments from institutions in several countries. Ground-based astronomers supported observations. Deep Space Network stations in California, Spain, and Australia connected Earth to the spacecraft. The mission could be described as one vehicle, but its effective body extended around the world. A transmitter at Saturn depended on antennas across Earth. A probe built in Europe depended on an American orbiter to relay data. An Italian antenna served every instrument. Planetary exploration operated through interdependence. This made failures politically and personally complicated, but success belonged broadly. When Huygens landed, scientists in Darmstadt, Pasadena, and other centers waited for confirmation. When Cassini entered Saturn orbit, teams across agencies shared the result. When the final signal vanished, decades of work ended at once for people in many countries. Long missions create communities around a machine. They also outlive some of their builders. Cassini was conceived before many later team members began their careers. Some scientists joined after launch. Students grew into investigators while the spacecraft remained at Saturn. The mission spanned technological eras. It launched before smartphones, before social media, and before many households had fast internet. By the grand finale, raw images could spread around the world within hours. The spacecraft itself could not be upgraded physically. Its computing and memory remained products of the 1990s. Software updates extended capability, but no engineer could replace a camera or add a larger storage device. A machine built before launch continued answering questions no one had thought to ask. This mismatch between old hardware and new questions is one of deep space exploration's defining features. An instrument must be broad enough to recognize the unexpected. Cassini's mass spectrometer was not designed specifically to search for hydrothermal chemistry at Enceladus because no known plume existed when it was built. Its dust analyzer was not designed as an ocean sampler. They became those things because the world presented a new experiment. The spacecraft's ability to adapt depended on operations. After the plume discovery, trajectories changed. Instruments received new priorities. Teams developed plume crossing strategies. Data analysis methods evolved. A rigid mission would have observed the unexpected and continued past it. Cassini returned. The extensions were essential. The original Prime mission ran from 2004 to 2008. The Equinox mission continued through 2010. The Solstice mission extended operations to 2017. The names described seasonal milestones. Equinox occurred when the Sun crossed Saturn's ring plane. Solstice brought maximum northern illumination. The extensions also described a deepening relationship. By then, Cassini had traveled billions of kilometers relative to the Sun, executed millions of commands, and built an archive containing hundreds of gigabytes of measurements and nearly 500,000 photographs. Statistics outline the scale. They do not explain what changed. Before Cassini-Huygens, Titan was a hazy moon with an unknown surface. Afterward, it was a world with dunes, rivers, rain, polar lakes and seas, seasonal weather, a buried ocean, and one human-made probe resting on its ground. Before Cassini, Enceladus was a small, bright moon with signs of past geology. Afterward, it was an active ocean world releasing salty water, organics, silica, hydrogen, and other material into space. Before Cassini, Saturn's rings were known to be structured. Afterward, they were seen as a living disk of waves, moonlets, spokes, collisions, propellers, vertical walls, and exchange with the planet. Before Cassini, Saturn's seasons were inferred from distant observations. Afterward, one spacecraft had watched nearly half a Saturnian year. Before Cassini, the search for habitable environments focused strongly on planets and on Jupiter's moon Europa. Afterward, tiny Enceladus became a leading target, and Titan expanded the meaning of organic planetary chemistry. Its impact was conceptual rather than merely descriptive. It did not solve everything. A small icy moon could contain an ocean in contact with rock. A moon far beyond the traditional habitable zone could provide chemical energy. A hydrocarbon world could possess an Earth-like weather cycle using different materials. A ring system could record oscillations from inside a giant planet. A moon's gravity could act as a spacecraft engine for 13 years. A final act of destruction could be an act of preservation. The mission changed how planetary scientists plan time. Voyager showed the power of a flyby. Cassini showed the power of residence. A system as complex as Saturn cannot be understood during one encounter because weather changes, seasons turn, plume output varies, ring patterns evolve, and new discoveries require return visits. Time creates context. One image shows a cloud. A decade shows climate. One plume crossing detects molecules. Repeated passes separate stable chemistry from instrumental uncertainty. One ring view shows structure. Equinox shadows reveal height. Solstice reveals seasonal change. The lesson influenced later missions to the outer solar system. Orbiters and long-duration tours became the goal where technology and budgets allow. Future studies of ocean worlds increasingly emphasize repeated sampling, geophysical context, and planetary protection. Cassini also changed the relationship between planned objectives and unexpected science. Titan was the planned center. Enceladus became the surprise that redirected attention. A great mission must arrive with questions and remain capable of discovering that the most important question was missing. The instruments need breadth. The operations need flexibility. The mission duration needs enough margin for surprise. Cassini possessed all three. Its limitations are equally instructive. No instrument could determine whether Enceladus's chemistry was biological. Radar coverage of Titan remained incomplete. The deep interior of Saturn could be constrained but not directly seen. The ring age remained debated. Mimas's possible ocean emerged more clearly only through later analysis. A mission that changes everything often reveals how much the next mission must do. Cassini's discoveries created destinations. Enceladus now calls for instruments capable of measuring isotopes, complex molecular patterns, chirality, and possible cell-like structures in plume material. Titan calls for mobile exploration across dunes and impact deposits, linking atmospheric organics with surface chemistry. Saturn's rings call for continued modeling and future observations that can distinguish young formation from ancient survival. The giant planet itself calls for deeper atmospheric and interior probes. Cassini's archive does not close Saturn. It provides the map of where ignorance has become most interesting. The archive remains available to researchers who were not part of the original mission. Raw measurements can be recalibrated. New laboratory experiments can be compared with old spectra. Improved computer models can reinterpret gravity, radar, and magnetic data. Machine learning methods can search image collections for subtle patterns, though every result still needs physical validation. Cassini's science continues without new transmissions because data can outlive hardware. The phosphorus in Enceladus's ocean was identified years after the spacecraft ended, through continued analysis of ice grain measurements. Other compounds and processes have been recognized in archived data long after collection. Mimas's ocean case strengthened through later modeling. Saturn's diffuse interior became clearer through ring seismology and mission measurements analyzed together. The date of discovery is not always the date of observation. Sometimes a spacecraft sees something before science has the language or method to recognize it. This gives archives a quiet suspense. A signal may already exist without an accepted interpretation. The future of Cassini science depends on questions no one has asked yet. But the greatest legacy is not a hidden answer waiting in one spectrum. It is the structure of the known Saturn system that Cassini built. Scientists can argue about details because the broad geography is now real. Titan has seas. Enceladus has a global ocean and plumes. The E ring is fed by Enceladus. The F ring is sculpted by moons and collisions. Saturn's winds extend deep. The magnetic field is unusually aligned. The moons migrate. The rings exchange material with the atmosphere. These are no longer imaginative possibilities. They are the starting conditions for new science. Cassini also changed Saturn for people who never analyzed data. Its images entered classrooms, books, screens, and memory. A backlit Saturn surrounded by glowing rings became one of the defining portraits of the solar system. Huygens's orange view of rounded ice stones made Titan's surface tangible. Enceladus's fountains turned a small moon into an active world. Earth seen through Saturn's rings placed human scale inside planetary scale. The images carried no equations, but they changed what people could picture. Before photography from spacecraft, other worlds were reconstructed from telescopic light and artistic imagination. Cassini returned actual shadows, actual coastlines, actual storms, actual cliffs. The distinction matters emotionally and scientifically. A photograph is also measurement. Angle, brightness, wavelength, time, and geometry recorded together. Beauty and evidence occupied the same frame. The mission's duration created a personal timeline for many observers. A child could watch the launch in 1997, the Saturn arrival in 2004, Huygens land in 2005, Enceladus become an ocean world, and the grand finale in 2017. The spacecraft remained active across school years, careers, marriages, births, illnesses, and deaths. For the mission team, this span was even more direct. People spent major portions of working lives planning a sequence that lasted minutes. Engineers who built systems before launch listened to their final signal 20 years later. Scientists who proposed instruments in youth received mature archives near retirement. Cassini became part machine and part shared calendar. This human scale should not be confused with the machine itself. Cassini did not feel lonely at Saturn. It did not know Titan, fear the ring gap, or choose sacrifice. People use emotional language because missions organize human attention across time. The spacecraft was hardware following commands and physical laws. Its meaning arose from what people built it to do and what nature allowed it to discover. That distinction does not diminish the achievement. It makes its human origin clearer. No heroic machine saved itself. Teams anticipated failure, built redundancy, navigated across billions of kilometers, corrected mistakes, extended operations, and chose a responsible end. The mission was human intelligence made durable enough to work where humans could not go. What Cassini changed most deeply was not one fact about Saturn. It changed the categories used to think about worlds. Before the mission, the phrase habitable zone usually directed attention toward planets at distances from a star where sunlight might allow liquid water on a surface. That idea remains useful. Earth's climate depends on solar energy, atmosphere, orbit, and geology. But Saturn lies far beyond the region where sunlight can keep exposed water liquid. Cassini showed that distance from a star is not the only way to build a potentially habitable environment. Tidal gravity can flex a moon. Friction can create heat. Ice can insulate an ocean. Water can contact rock. Chemical reactions can supply energy without sunlight. Enceladus made this chain observational rather than hypothetical. The surface remains frozen. The habitat, if one exists, lies inside. This shift enlarged the search for life. A world need not resemble Earth at the surface. It may hide its most important environment under kilometers of ice. The outer solar system contains many icy moons. Some are large enough to retain internal heat. Some are flexed by giant planets and neighboring moons. Some contain antifreeze compounds such as salts or ammonia that lower water's freezing point. Cassini showed that these factors can operate in a body as small as Enceladus. Smallness no longer meant geological death. Brightness no longer meant simplicity. An apparently frozen moon could be an active ocean world. Titan changed a different category. Astrobiology often searches for liquid water because all known life depends on it. Titan's surface is too cold for liquid water, yet it supports a complex cycle of another liquid and manufactures enormous quantities of organic compounds. This makes Titan neither conventionally habitable at the surface nor biologically irrelevant. It is a natural laboratory for chemistry in which carbon-rich molecules accumulate over geological time. Some organics may mix with transient liquid water created by impacts or cryovolcanic processes. Others may be transported toward the internal ocean. The pathways remain uncertain. Cassini showed that prebiotic interest does not require a warm blue planet. A dark dune under orange haze can be chemically important. The mission therefore expanded two frontiers at once. Enceladus broadened where liquid water habitability can exist. Titan broadened where complex organic planetary chemistry can develop. Together, they changed the priorities of future exploration. This transformation also affected planetary protection. Before Cassini, the idea of contaminating Enceladus carried less urgency because the moon's present habitability was unknown. After the plume discoveries, a future accidental impact had a different meaning. Earth microorganisms are unlikely to survive every stage of spaceflight: impact, radiation, and transfer through ice. Unlikely is not the same as impossible enough to ignore. Planetary protection does not assume that contamination will certainly create an ecosystem. It aims to preserve scientific integrity and avoid introducing terrestrial biology into environments that may be able to support it. The planned final plunge converted a scientific discovery into an operational obligation. Cassini had made Enceladus important enough to change how Cassini itself was allowed to end. This is a rare feedback in exploration. A mission learns something about a world. The new knowledge changes the ethical rules governing the mission. The spacecraft becomes responsible for the significance it revealed. Titan strengthened the same logic. Its surface chemistry may preserve natural processes that contamination could confuse. Its buried ocean remains difficult to access, but long-term protection matters. Cassini entered Saturn rather than risk either moon. The decision demonstrates that planetary protection is not only a rule imposed before launch. It can evolve with discovery. The mission also transformed the concept of sampling. To study an ocean, one usually imagines drilling through ice or landing beside a vent. Enceladus offers another method. The moon ejects material. A spacecraft can fly through it. Cassini's instruments collected gas and ice impacts while moving at high speed. They could determine broad composition, but often fragmented large molecules and lacked life detection specificity. The next mission can be designed around the plume from the beginning. It can fly more slowly relative to the particles, use higher resolution mass spectrometry, preserve fragile organics, measure isotopes, and search for patterns associated with biology. Cassini turned an engineering impossibility reaching an alien ocean, into a sample collection problem. The ocean travels upward. The mission only needs to meet it. This insight is among the clearest examples of exploration creating a new experimental strategy. The change reached beyond Saturn. When scientists study Europa, they now ask whether plumes may provide access to its ocean. When they consider other icy moons, they look for exchange between interior and surface. Ocean world missions increasingly combine geophysics, chemistry, geology, and astrobiology. A measurement of water alone is not enough. Scientists ask whether water contacts rock, how long the ocean has existed, what energy gradients are available, and whether surface oxidants can reach the interior. Cassini made habitability a system question. The same systems approach changed ring science. Before detailed orbital observations, ring features could be cataloged by position. Cassini followed them through time. A sharp edge became a product of moon resonances, particle collisions, and self-gravity. A gap contained waves and small moons. A spoke connected dust charging to the magnetic environment and season. A propeller revealed an unseen embedded body. A density wave measured ring mass locally. A spiral pattern could record an impact event or an internal oscillation of Saturn. The rings became both subject and instrument. This is a larger methodological lesson. Planetary systems often contain natural detectors. A moon's orbit records tides. A ring wave records gravity. An atmosphere records sunlight and interior heat. A plume records ocean chemistry. A magnetic disturbance records escaping gas. Cassini learned to read one part of the Saturn system through another. The mission's scientific power came not only from instrument sensitivity, but from relationship. This relational view is increasingly important for exoplanets. Telescopes observing distant planetary systems usually cannot see surfaces directly. They infer worlds from starlight, orbital motion, atmospheric spectra, and interactions. Cassini provides a nearby example of how complex one planetary system can be. A giant planet influences moon orbits. Moons feed rings and magnetospheres. Rings reveal interior oscillations. Atmospheres exchange material with space. Seasonal changes alter chemistry. A single unresolved point of light around another star may contain comparable complexity. Saturn teaches caution. An exoplanet spectrum is not one isolated atmosphere. It may be influenced by rings, moons, impacts, clouds, seasons, and interior processes. Detailed solar system exploration provides the physical vocabulary needed to interpret distant systems. Cassini therefore changed more than Saturn science. It changed comparative planetology. It showed how a hydrogen-rich giant behaves differently from Jupiter despite superficial similarity. Saturn's lower density, deep winds, magnetic alignment, ring system, and moon architecture create a distinct planetary environment. It showed that two nitrogen-rich atmospheres, Earth's and Titan's, can produce radically different surfaces because temperature and chemistry differ. It showed that two small icy moons, Mimas and Enceladus, can hide very different levels of visible activity while perhaps both containing oceans. It showed that surface appearance alone can mislead. A cratered moon may be internally young. A smooth moon may be active. A dark hemisphere may result from imported dust and thermal feedback. A bright ring may not reveal its age simply. Comparisons become stronger when exceptions appear. Cassini also altered engineering practice. Its tour demonstrated how repeated gravity assist from a moon can replace vast amounts of propellant. Titan did not simply provide occasional help. It controlled the architecture of the mission. Navigators could choose the side and altitude of a flyby to bend Cassini differently. A small change at Titan propagated into a new orbit around Saturn. This allowed one spacecraft to visit targets spread across a huge system. Future mission designers gained a mature example of moon-assisted tours. The method requires precision and patience. A flyby that optimizes one scientific target may compromise another. The path through a planetary system becomes a long sequence in which every encounter sets the next. Cassini's 294 orbits were therefore not repetitive. They were chapters in one gravitational design. The mission proved the value of planning flexibility over decades. The Prime Tour had one set of priorities. New discoveries required new flybys. Extensions used remaining propellant differently. The final sequence was planned while spacecraft health, fuel, scientific goals, and protection obligations evolved. Operations were not simply the execution of a frozen plan written before launch. They were continuous scientific adaptation. This is crucial for missions traveling to places where surprises are expected. A spacecraft cannot carry every possible instrument. A schedule cannot anticipate every discovery. But hardware can be designed with broad capability, software can be updated, and trajectories can preserve options. Cassini's most important target after arrival was not its most important target before launch. That fact may be the mission's strongest argument for exploration itself. Remote observations and theory tell us where to look. Only arrival reveals what the questions truly are. The mission also demonstrated the limitations of cost arguments based only on launch and nominal duration. Cassini-Huygens cost billions of dollars over decades. That figure is large and deserves scrutiny. But the scientific return continued far beyond the original 4-year mission and continues after the spacecraft's destruction. The same hardware studied a giant planet, rings, magnetosphere, dozens of moons, an atmosphere during descent, surface liquids, subsurface oceans, hydrothermal chemistry, and planetary seasons. The archive supports generations of research. One cannot reduce value to a price per image or paper. The mission built instruments, international partnerships, navigation expertise, planetary protection practice, and public knowledge. Its cost belonged to Earth's economies, paying engineers, scientists, manufacturers, launch teams, and institutions. The spacecraft carried only a fraction of that material wealth away. The knowledge returned. This does not mean every large mission is automatically justified. It means evaluation must include longevity, adaptability, and the scientific network created around it. Cassini endured because its discoveries continued to outrun expectations. Each extension had to earn support. Enceladus, Titan, Seasons, Rings, and the grand finale provided reasons. The spacecraft became more valuable with age because the time baseline grew. An observation after 10 years could be compared with one made at arrival. This compounding value is rare in machines. Most hardware becomes obsolete. A planetary orbiter can become scientifically richer as the environment changes around it. Cassini's age was an instrument. The mission changed public ideas about failure as well. The Huygens receiver error did not erase the landing. Missing data remained a real loss, documented rather than hidden. Ground observations recovered part of the wind experiment. Other instruments returned historic results. The incident showed that exploration can be imperfect and still transformative. Cassini itself entered safe mode on several occasions, when onboard systems detected a problem and placed the spacecraft in a protective configuration. Teams diagnosed causes across interplanetary distance and returned to science. Some instruments suffered limitations or interruptions. Power declined. Software had to accommodate aging equipment. The mission did not succeed because nothing went wrong. It succeeded because failures were anticipated, detected, contained, and worked around. Redundancy mattered. Testing mattered. Institutional memory mattered. The spacecraft's longevity was engineered rather than miraculous. Even the final destruction depended on reliability. A spacecraft too damaged to control could not protect the moons. Cassini remained capable of navigation and transmission to the end. The responsible disposal was possible because the machine had survived. Its last science was not a consolation prize. The atmosphere measured during entry had never been sampled directly at those altitudes. The final signal carried unique data while the spacecraft was becoming unrecoverable. The mission treated every remaining second as scientifically useful. That discipline is part of what the grand finale symbolized. The word finale can imply performance, and the name was deliberately dramatic. But the dives were not theater designed only for attention. They filled a region of scientific ignorance. The gap between rings and atmosphere had never been crossed. The gravity field was strongest there. The magnetic field could be measured most closely there. Ring material could be sampled there. The final orbit had value because it was dangerous. Once no future mission phase needed protection, risk tolerance changed. Engineers could send Cassini where they would never have sent it during the prime mission. End-of-life planning became an opportunity to explore the edge of survivability. This strategy has influenced thinking about other missions. A spacecraft nearing disposal may perform orbits or encounters too risky earlier, provided planetary protection and debris concerns are addressed. The final phase can be designed years in advance as serious science rather than an afterthought. Cassini turned the concept into one of the most memorable mission endings in history. Yet memory can simplify. The grand finale should not overshadow the 13 years that made it meaningful. Without routine Titan flybys, there would be no final Titan gravity assist. Without Enceladus, the plunge would not carry the same protective necessity. Without seasonal observations, the extensions would not have built a climate record. Without years of navigation experience, the gap dives would have been too risky. The ending condensed the entire mission. Titan guided. Enceladus justified protection. Saturn received the spacecraft. The Deep Space Network listened. Everything returned to the system that Cassini had learned to navigate. Consider what would be missing if the insertion burn in July 2004 had failed. Cassini might still have returned valuable flyby data. Huygens could not have been delivered properly to Titan. There would have been no long radar map of the surface. No 13-year seasonal record. No repeated Enceladus plume crossings. No grand finale. No day the Earth smiled. No 294 orbits. The spacecraft would have passed Saturn once and continued into darkness. This counterfactual reveals the importance of capture. Orbit transforms speed into time. A flyby offers proximity. An orbit offers return. Return made Cassini's discoveries cumulative. The first Titan radar image was incomplete, but later swaths added coastlines and dunes. The first Enceladus anomaly was ambiguous, but later encounters added plume images, salts, gravity, silica, and hydrogen. The first ring observation showed structure, but equinox revealed vertical relief, and the grand finale measured gravity and inflow. The first Saturn atmosphere images showed weather, but years revealed seasons and a planet encircling storm. Each answer became the reason for another encounter. Cassini did not discover Saturn once. It discovered the system repeatedly as context grew. The mission's architecture also demonstrated how much can be learned without bringing material home. Cassini returned no sample to Earth. Huygens sent no physical object back from Titan. Every result traveled as encoded radio waves. A detector counted particles, measured energy, recorded brightness, or registered a changing field. Electronics converted the measurement into numbers. The spacecraft stored those numbers and transmitted them. Antennas on Earth reconstructed the data from a signal weaker than ordinary noise. From that chain came oceans, seas, storms, cores, and chemistry. This is one of remote exploration's most remarkable translations. Nothing wet arrived from Enceladus, yet scientists could identify salts in its ocean. No bottle of Titan rain reached Earth, yet methane weather could be mapped. No ring particle sat in a laboratory, yet particle sizes, composition, density, and waves could be constrained. No probe reached Saturn's deep interior, yet the planet's gravity and ring oscillations revealed structure. The mission converted indirect measurement into physical worlds. A sample return mission can answer questions remote instruments cannot. Laboratories on Earth are larger, reparable, and continually improved. But Cassini showed the immense reach of careful in situ and remote sensing when return is impossible. It also showed why one must understand the measurement process itself. A mass spectrum depends on how molecules enter and fragment inside an instrument. Radar brightness depends on surface roughness, angle, and dielectric properties. A color image depends on filters, exposure, calibration, and processing. A gravitational inference depends on trajectory models and contributions from multiple bodies. Data does not arrive with its interpretation attached. The mission's discoveries required experiments on Earth, numerical models, comparison among instruments, and arguments that sometimes lasted years. The public image of a lone spacecraft can obscure this second half of exploration. Cassini gathered evidence. Human communities turned evidence into knowledge. That division of labor continues long after the spacecraft is gone. Another quiet achievement was the mission's ability to preserve uncertainty without losing direction. When the Enceladus plume appeared, scientists did not immediately announce life. When Titan's radar showed dark regions, they tested whether the surfaces truly behaved like liquid. When gravity suggested interiors, alternative models remained in discussion. When ring mass supported youth, other age mechanisms were examined. The mission's reputation rests partly on discoveries that survive caution. Wonder did not require certainty before evidence. Certainty did not require pretending every question was closed. This balance matters because Saturn invites spectacle. The rings are visually overwhelming. Titan resembles an early Earth in some chemical respects. Enceladus offers an accessible ocean. Each can attract language stronger than the data. Cassini's best legacy is not exaggeration, but the fact that precise statements are already extraordinary. There is a global ocean inside a moon 500 kilometers across. There are stable hydrocarbon seas beneath an orange nitrogen atmosphere. There are waves and rings generated by oscillations inside a giant planet. There are particles from a hidden sea entering a planetary ring. These conclusions need no fictional addition. Their power lies in being real. The meaning of 13 years at Saturn can be understood through this accumulation. 13 years at Saturn mattered because the same spacecraft could compare the system with its own past. A new instrument was not required to notice that a cloud had moved. A new mission was not required to see the North Pole in sunlight. The baseline already existed. Time converted observation into change. This is especially important for a planet where one season lasts more than 7 Earth years. Cassini arrived during one arrangement of light and shadow and departed during another. The rings first cast winter darkness across the north. At equinox, the shadows became narrow. By northern summer, the south lay beneath the broad ring shadow. Atmospheric chemistry followed. Titan's clouds followed. Temperatures followed. Auroras and hazes responded. The mission observed a planetary system breathing at a pace slower than most human projects. The spacecraft's survival allowed human attention to slow down with it. Cassini also changed the perceived boundary between geology and weather. On Titan, rain shapes rock-hard water ice. On Enceladus, ocean water becomes snow and ring particles. In Saturn's rings, orbital motion creates temporary structures that resemble weather in a disk. In Saturn's atmosphere, storms lift chemistry from depths. On Iapetus, dust and sunlight redistribute ice across hemispheres. The categories used on Earth, surface, atmosphere, hydrology, geology, overlap differently elsewhere. Cassini made these alien combinations concrete. It also revealed that activity can be subtle. No volcano towered above Enceladus in the terrestrial sense. Thin fractures vented material along long curtains and jets. No ocean wave was required to prove Titan's seas. Radar smoothness, shorelines, depth sounding, and dielectric properties converged. No drill reached Mimas. A wobble and later orbital modeling suggested the hidden layer. No probe entered Saturn's core. Gravity and ring waves constrained the interior. Planetary science often advances through indirect evidence. Cassini taught the public to see inference as discovery. A hidden ocean is real even when no camera photographs its surface. The confidence comes from measurements agreeing under physical models. The mission's strongest conclusions were mosaics of evidence. This makes scientific uncertainty important rather than embarrassing. Ring age remains debated because multiple processes can explain brightness and pollution. Titan's methane source remains uncertain because several reservoirs and climate histories are possible. Mimas's ocean may be young, but its formation history remains under study. Enceladus is habitable by known criteria, but habitation is unproven. Saturn's magnetic alignment is measured, but the dynamo mechanism remains puzzling. Cassini transformed the field partly by defining what is still unknown with greater honesty. Before a mission, ignorance can be broad and featureless. Afterward, ignorance has shape. Scientists know which isotope ratio is missing, which part of a surface needs mapping, which model parameter controls ring age, which measurement could distinguish a rocky core from a diffuse one, and which instrument could test for life in plume grains. Specific ignorance is progress. It can be engineered against. Future missions can be built around it. The same principle applies to the mission archive. A spectrum without sufficient resolution cannot be made infinitely precise later. A region never imaged cannot be reconstructed from imagination. Archives preserve what instruments actually measured, including noise and limitation. Yet new context changes old data. When laboratory experiments show how silicon nanoparticles form, Cassini's grains become evidence for hot water. When phosphate signatures are recognized, archived impacts become ocean chemistry. When better models connect libration with an ocean, old tracking data reveal a new moon. The archive is finite and generative at once. It cannot replace a new spacecraft. It can continue to surprise until questions exceed its resolution. Cassini's science papers now number in the thousands, written by teams across generations. Some use one instrument. Others combine many. Some focus on a single storm, ring wave, crater, or molecule. Others reconstruct global systems. This range reflects the mission's design. A large flagship mission can support both broad survey and narrow detail. One camera image may become a geological map. One radio occultation may define an atmospheric layer. One dust impact may contain fragments of a molecule from an ocean. One magnetometer deviation may redirect an entire mission. The scale of consequence cannot always be predicted from the size of a signal. The Enceladus discovery began with a disturbance that might have been treated as a technical complication. Instead, scientists asked what physical source could create it. Curiosity turned anomaly into ocean. Cassini's legacy, therefore, includes a habit of attention. The unexpected should not be discarded merely because it lies outside the original plan. It should be tested. Instruments should overlap enough to challenge one another. Operations should preserve opportunities for follow-up. Archives should retain data and forms future researchers can inspect. These habits are as important as any individual result. The mission's international nature strengthened that habit. Different teams brought different expectations. Radar scientists saw Titan through microwave reflection. Atmospheric scientists read haze and temperature. Geologists interpreted channels and dunes. Plasma physicists studied interactions that imaging alone could not reveal. No single discipline owned Saturn. Complex worlds require scientific languages to meet. Cassini-Huygens was built physically as an assembly of contributions and intellectually as an assembly of methods. The spacecraft's name itself joined two observers separated by centuries and nationality. Future spacecraft will return. They will carry better detectors, more capable computers, and questions Cassini created. Some may fly through Enceladus's plume, specifically searching for biosignatures. Some may land or fly on Titan. A future Saturn probe may descend through the atmosphere and measure composition below the cloud tops. Ring and Moon missions may revisit unresolved origins. When they arrive, they will not begin from Voyager-era uncertainty. They will inherit Cassini's maps, seasons, hazards, and mysteries. This inheritance shortens the distance between arrival and understanding. A new Titan mission can choose a landing region because radar revealed dunes and impact structures. An Enceladus mission can optimize plume crossings because Cassini measured jets and orbital variation. A Saturn probe can target missing noble gas and deep atmosphere measurements because Cassini defined what remote sensing cannot supply. The next missions begin where Cassini ended. That is how exploration becomes cumulative across generations. One spacecraft cannot answer every question, but it can change the starting point for all that follow. The mission also provides a standard against which future projects will be judged. Not every mission can last 13 years at its target. Not every system offers a Titan for gravity assists. Budgets and technology differ. The lesson is not to copy Cassini mechanically. It is to design for depth when the target demands it, to preserve adaptability, to plan a responsible end, and to treat time as scientific value. A short mission may be correct for one question. A long residence may be essential for another. Saturn required residence. The scale of Cassini's transformation can now be stated precisely. Cassini changed the known geography of Titan. It changed the biological importance of Enceladus. It changed estimates and debates about the rings. It changed models of Saturn's atmosphere and interior. It changed the inventory of ocean worlds. It changed planetary protection decisions. It changed future mission designs. It changed the public image of the outer solar system. And it changed the questions scientists ask when they encounter a small, icy body that appears quiet. Perhaps the most important change is that apparent stillness is no longer trusted. A bright frozen surface may conceal water. A cratered shell may conceal youth. A smooth ring may conceal waves and embedded moons. A pale atmosphere may conceal planet-scale storms. A haze may conceal seas. Cassini taught suspicion of simplicity. The closer it looked, the more active Saturn became. This is not unique to Saturn. Every successful planetary mission has found complexity where distance created smoothness. Mars gained valleys, minerals, weather, and layered history. Jupiter gained storms, auroras, and ocean moons. Pluto gained glaciers and haze. Distance erases detail. Exploration restores it. Cassini restored Saturn with unusual patience. Return once more to July 2004. The spacecraft is behind the planet from Earth's point of view. The engine is burning. No one yet knows about the plume chemistry, Titan's coastlines, ring seismology, or the final gap dives. The future mission exists only as possibility inside one maneuver. The engine performs correctly. A radio signal returns. Cassini is in orbit. From that moment, 13 years begin to unfold. Huygens separates. A probe falls through orange cloud. Radar finds seas. A magnetometer notices a disturbance. Plumes rise into sunlight. A storm circles Saturn. Ring shadows narrow to a line. The North Pole changes color. Tiny moons reveal impossible shapes. A camera turns back toward Earth. Titan bends the orbit one final time. Cassini dives through the ring gap. The last signal leaves Saturn. All of those events depend on capture, endurance, and return. The mission's greatness lies not only in distance traveled, but in attention sustained. For 13 years, people asked the machine to look again. Look at Titan in another season. Look at Enceladus from lower altitude. Look at the rings when sunlight is edge-on. Look beneath the haze with radar. Look inside Saturn through gravity. Look once more before the end. The answers accumulated until the Saturn system no longer resembled the one Cassini had been designed to visit. The mission arrived at a planet with rings and moons. It left behind an interconnected system of weather, oceans, chemistry, tides, migration, and evolving ice. The final radio signal has long since passed Earth and continued outward into space, becoming weaker as it expands. It carried no farewell sentence. It carried telemetry and science. Human beings supplied the farewell. Saturn supplied the discoveries. Cassini supplied the years between them. There is another way to understand those years. Cassini transformed distance into familiarity without making Saturn ordinary. At the beginning of the mission, every close view was new. A small moon appeared as a handful of pixels and then became a landscape. A bright ring edge became a sequence of particles and waves. A haze-covered globe became a world with weather and shorelines. As familiarity grew, the sense of mystery did not shrink. It became more precise. Titan's seas could be mapped, but their depths and long-term cycles raised new questions. Enceladus's ocean could be confirmed, but the origin of its chemistry and the possibility of life remained open. Saturn's rings could be weighed, but their age became a debate rather than a settled date. The magnetic field could be measured more closely than ever, yet its alignment made the deep rotation harder to read. This is an important difference between science and the ending of a puzzle. A solved puzzle becomes quiet. A well-studied world becomes louder with better questions. Cassini did not remove wonder by explaining Saturn. It replaced vague wonder with physical wonder. A storm encircling a giant planet is more extraordinary when its temperatures and chemistry can be measured. An ocean beneath ice is more extraordinary when salts and hydrogen are detected directly. A ring wave is more extraordinary when it can be connected to an oscillation inside Saturn. Precision does not make nature smaller. It makes the scale of the mechanism visible. The mission also changed the meaning of remoteness. Saturn remained physically far away. Every command and reply crossed a delay measured in hours for a full conversation. A problem could not be handled with a technician standing beside the machine. No spare part could be delivered. Yet the spacecraft's repeated observations created a kind of practical closeness. Teams knew the timing of Titan's passes, the response of instruments, the geometry of ring shadows, and the habits of the spacecraft. They could predict when a moon would enter eclipse or when a radio signal would pass through an atmosphere. Remoteness became manageable through models and routine. This is one of engineering's quiet victories. The solar system did not become nearby. Human planning became capable of operating far away. That capability depends on trust built from many layers. The orbit model must be right. The clock must be right. The command sequence must be right. The spacecraft must interpret it correctly. The antenna must point toward Earth. The deep space network must be listening. The data must be decoded. The instruments must be calibrated. The scientific interpretation must survive comparison with alternatives. A finished image can hide this chain. Cassini's mission is remarkable because the chain remained intact across decades. It began with proposals and political agreements before the spacecraft existed. It continued through manufacturing, launch, cruise, orbit insertion, extensions, and final disposal. It continues now through archives and interpretation. The mission therefore has no single date of achievement. Launch was necessary. Arrival was necessary. Huygens was necessary. The Plume discovery was necessary. The grand finale was necessary. So was every quiet day when a heater, computer, transmitter, and navigation plan simply worked. Large missions are remembered through dramatic moments because memory needs scenes. Their real success is continuity between scenes. Cassini also offers a caution against exaggeration. No scientific mission literally changes every field or every belief. Saturn continued obeying the same physics before and after the spacecraft arrived. What changed was the human map of possibility. Ocean worlds became central rather than peripheral. Titan became a world of active surface liquids rather than a hidden orange sphere. Ring systems became records of planet interiors and ongoing evolution. Planetary protection became tied directly to discoveries made during the mission. A mission ending could be designed as both scientific campaign and ethical disposal. These changes are specific enough to matter and broad enough to influence decades. They reach textbooks, funding priorities, mission concepts, laboratory experiments, and public imagination. A child seeing Enceladus's plume in a Cassini image may later design an instrument to sample it. A student analyzing Titan radar may help fly a future rotorcraft. An engineer who studied the grand finale may plan the risky final orbits of another mission. Knowledge moves through people in ways data tables cannot record. This is how one spacecraft continues after destruction, not as a personality or a ghost, but as inherited method. The next team does not begin from zero. It inherits mistakes, solutions, measurements, and confidence. Cassini's receiver problem at Huygens becomes a lesson in end-to-end testing. Its Titan gravity assists become a lesson in tour design. Its plume flybys become a lesson in adaptive science. Its final plunge becomes a lesson in protection and disposal. Its archive becomes a lesson in preserving measurements beyond the careers of the people who collected them. The meaning of Cassini's 13 years was already clear. What remained was to complete the mission responsibly. All of those discoveries and lessons now converged on the last phase of the mission. The prime mission had surveyed. The equinox extension had compared. The solstice extension had watched change and prepared the final experiment. Fuel, not scientific exhaustion, determined the end. Cassini used hydrazine for attitude control thrusters and bipropellant for major maneuvers. Propellant estimates always contained uncertainty because tanks could not be opened or weighed in flight. Engineers tracked usage through pressure, temperature, burn performance, and models. Eventually, control would become unreliable. A dead spacecraft in Saturn orbit might remain for years or centuries before chaotic perturbations sent it toward a moon. No team could guarantee permanent avoidance after communications ended. The discovery of Enceladus changed the ethics of disposal. Before the plume, an uncontrolled collision with a small icy moon might have seemed scientifically unfortunate, but biologically unimportant. After the ocean and hydrothermal evidence, contamination became unacceptable. Titan's chemistry and hidden ocean also demanded protection. The end had to be planned while Cassini was still healthy enough to execute it. In 2010, the mission adopted the long path toward the grand finale. The final years would consume propellant productively, complete additional moon flybys, watch Saturn approach northern solstice, and then use Titan to place Cassini into a sequence of unprecedented orbits. Before the final gap dives, the spacecraft entered ring grazing orbits in late 2016. It passed near the outer edge of the main rings, observing ring structure and small moons at close range. Pan's strange shape emerged. The F-ring changed beneath it. The spacecraft moved closer to danger while still returning data. Then came the last targeted close encounter with Titan in April 2017. Titan's gravity changed Cassini's velocity relative to Saturn by hundreds of meters per second and placed it on a ballistic path toward the region between the planet and the rings. The moon that had guided the mission for 13 years delivered it to the final phase. After that flyby, the ending was physically committed. Small course corrections could refine details, but the September atmospheric entry could no longer be avoided through ordinary operations. The grand finale began. The gap between Saturn's atmosphere and the inner edge of the D ring is thousands of kilometers wide, but width alone did not make it safe. The region had never been sampled. Dust or fragments too small to see could damage Cassini at high relative speed. For the first dive, the spacecraft used its high-gain antenna as a shield, orienting the dish in the direction of travel. This protected sensitive equipment behind it, but prevented some observations during the riskiest part. The spacecraft crossed the ring plane. No destructive impact occurred. The region was emptier than feared. For later dives, Cassini could use more instruments. 22 times, it passed through the gap. Each orbit lasted about a week. At closest approach, Saturn's clouds filled much of the view. The rings arched overhead. The spacecraft moved through a region that had been inaccessible through the entire mission. The grand finale was not only disposal. It was a new mission compressed into 5 months. Cassini measured Saturn's gravity with unprecedented precision. It sampled material falling from the rings. It studied the magnetic field close to the planet. It photographed atmospheric structures and the rings from unfamiliar angles. The last fuel became access. The danger became measurement. The end became one more discovery engine. The gravity data separated several effects that had been difficult to distinguish from farther away. Saturn's atmosphere does not rotate as one shell. Equatorial winds move faster than deeper material. Cassini's measurements showed that atmospheric flows extend thousands of kilometers below the visible cloud tops before the interior approaches more uniform rotation. The winds are not a painted surface phenomenon. They reach deep into the planet. At the same time, the spacecraft felt the pull of the rings. By subtracting Saturn's gravitational influence from the trajectory, researchers estimated ring mass more directly than before. The results supported a relatively low mass compared with some earlier models and strengthened arguments that the rings may be younger than the solar system. Yet the measurement did not settle age by itself. Mass constrains origin and evolution, but pollution, loss rates, and dynamical history still matter. Cassini made the debate quantitative. The magnetic field produced perhaps the most frustrating surprise. Planetary magnetic fields are generated by moving electrically conducting material deep inside. If a field is tilted relative to the rotation axis, its periodic signal can reveal the planet's internal spin. Saturn's field was aligned so closely with the axis that Cassini could not detect the expected tilt even during the nearest passes. The alignment challenged dynamo theory and kept the exact deep rotation period difficult to establish. The spacecraft moved closer than any predecessor and found that proximity did not guarantee simplicity. The ring-atmosphere interaction was equally unexpected. Material from the rings falls towards Saturn in a process broadly called ring rain. Earlier observations had detected some charged water-related particles guided by magnetic fields. During the grand finale, Cassini directly sampled a richer inflow containing water, methane, ammonia, carbon monoxide, molecular nitrogen, carbon dioxide, and organic material. The composition suggested that the innermost ring environment and upper atmosphere exchange material more actively than a clean picture of isolated rings would imply. The rate measured during the dives appeared high. Whether that exact rate persists over long times remains uncertain. Short-term structures, seasonal changes, and local conditions may matter. Once again, Cassini turned a fixed-looking object into an evolving system. The spacecraft also measured tiny dust populations in the supposedly empty gap. The region was not perfectly vacant, but it contained far less dangerous material than some engineers had feared. Every safe crossing confirmed the risk calculation while allowing new instruments to observe. The final orbits carried a strange, emotional rhythm. Each successful dive produced relief. Each completed orbit reduced the number remaining. The science team wanted the most daring measurements. The operations team had to protect the spacecraft long enough to reach the planned end. Both goals pointed toward the same final date. Cassini's last weeks included farewell images of moons it would never encounter again. Titan became a hazy globe receding in the distance. Enceladus appeared as a bright crescent above Saturn's rings. Small moons crossed the camera field. The images were scientific records and intentional goodbyes. A machine does not feel attachment, but the people selecting the targets did. On September 11th, Titan gave Cassini one final distant gravitational nudge. Mission engineers informally called this encounter the goodbye kiss. It adjusted the spacecraft's path so the next periapsis would enter Saturn's atmosphere. No engine failure was needed. No future command could rescue the spacecraft. The trajectory itself had become the disposal system. During the final days, Cassini transmitted stored images and other data to empty its recorder. The mission did not want unique observations trapped on board when the spacecraft was destroyed. The cameras took their last pictures on September 14th. The final portrait included Saturn, the rings, Titan, Enceladus, and the place where Cassini would enter the atmosphere. Then the imaging system was turned off. Cameras require pointing and data storage. During the plunge, instruments that could measure fields, particles, and gas in near real time received priority. The final approach occurred on Saturn's day side, near 10 degrees north latitude. Cassini entered the upper atmosphere at roughly 113,000 kilometers per hour. At first, gas density was extremely low. The spacecraft's thrusters fired small pulses to counter aerodynamic torque and keep the antenna pointed toward Earth. Data streamed through the high-gain dish. The ion and neutral mass spectrometer faced forward into the flow, sampling the atmosphere directly. Other instruments measured plasma, magnetic fields, and radiation. The atmosphere thickened. Thruster duty increased. A few percent. More. Near full output. The spacecraft had been designed for vacuum, not aerodynamic flight. Its broad antenna and irregular body created torque. Once the thrusters could no longer compensate, the antenna began to turn away. The radio link vanished. Cassini probably broke apart and burned within moments, like a meteor entering a world without a solid surface. Its metals, carbon, silicon, plutonium, and other materials dispersed into Saturn. The mission that had measured ring rain became a tiny artificial addition to the planet. On Earth, the final signal was received by the Deep Space Network station near Canberra, Australia. At JPL, controllers watched the carrier disappear. The time of lost match predictions. Precision remained to the end. Mission managers announced that Cassini had entered Saturn and completed its mission. There was applause, but not celebration in the ordinary sense. The team had succeeded completely by destroying the spacecraft they had protected for decades. This paradox gives the ending its power. A failed mission can be lost accidentally. Cassini was lost because it had discovered worlds worth protecting and because it remained controllable enough to choose its fate. The final plunge was evidence of success. The spacecraft completed 294 Saturn orbits. It performed 162 targeted moon flybys, including 127 at Titan and 23 at Enceladus. The final transmission also carried the mission's international character. A European probe had descended while an American orbiter relayed through an Italian antenna. Global radio telescopes had listened. The image of Huygens on Titan belongs to no one nation's sky. Cassini's plunge belonged to the same shared history. The spacecraft entered Saturn near local noon, but the last signal reached Earth through an Australian antenna. Mission Control in California received it. Scientists across Europe watched. The time was different in every location, while the event at Saturn had occurred more than an hour earlier. Deep space missions complicate the idea of now. When the signal vanished at JPL, Cassini had already been destroyed. When commands were sent during the mission, teams acted toward a future spacecraft state they could not yet see. Every operation required faith not in emotion but in models, clocks, navigation, and hardware. The spacecraft lived beyond immediate human response. Autonomy was modest by modern standards, but essential. Cassini protected itself during faults, executed stored sequences, and navigated through commands prepared for delayed reality. This temporal separation gives the final signal another meaning. The team did not witness destruction as it happened. They witnessed information completing its journey. The line on the monitor was not Cassini itself. It was the last causal connection between spacecraft and Earth. Once the carrier disappeared, no future data could leave Saturn from that machine. The silence was physical. A transmitter had stopped pointing. An atmosphere had overwhelmed the vehicle. No dramatic explosion could be seen from Earth. Only absence arrived. And yet the mission did not become absent. Its data filled archives. Its probe remained on Titan. Its discoveries reshaped mission plans. Its final trajectory protected moons. Its atoms entered Saturn. Different parts of Cassini continued in different forms. Huygens still rests on Titan's surface unless geological processes have shifted or buried it. It is silent, surrounded by cold nitrogen air and water-ice stones, under clouds that may someday release methane rain. Cassini itself cannot be recovered. The spacecraft dispersed high in Saturn's atmosphere. Material mixed into a planet with no solid surface on which a wreck could remain. The separation of orbiter and probe produced two endings. One machine landed and fell silent after transmitting from a moon. The other orbited for 13 years and burned in a planet. Together they completed the mission imagined decades earlier. Saturn continues without them. The North Polar hexagon turns. Winds move through pale clouds. Lightning flashes in storms. The rings orbit and collide. Prometheus disturbs the F ring. Enceladus vents ocean water into the E ring. Titan seas lie beneath orange haze. Methane clouds form and disappear. Iapetus carries its dark and bright hemispheres around the planet. Mimas hides whatever lies beneath its cratered shell. No spacecraft currently orbits Saturn to watch these processes continuously. Earth-based telescopes and space observatories continue remote measurements, but the intimate 13-year presence has ended. This absence shows what Cassini provided. For more than a decade, Saturn had a witness nearby. A human-built instrument could turn toward an unexpected storm, pass over a sea, cross a plume, or measure a ring edge. After 2017, the system returned to distance. The archive bridges the gap, but it cannot take a new image today. Its influence continues most effectively by making its own experience reusable. The spacecraft is gone, but the system it revealed remains active tonight, more than 1 billion kilometers away. Water still escapes Enceladus. Methane still moves through Titan's atmosphere. Ring particles still orbit, collide, and fall. Saturn still turns beneath its hexagonal jet. And somewhere in laboratories and archives on Earth, measurements gathered during those 13 years continue to become new knowledge. Good night.